Hello, yeah. Today's topic in machine learning using R is how to fit survival random forest using randomForestSRC. Okay. So basically, this is a random forest for survival data. And what we need is to install a package called randomForestSRC, and it's not very straightforward. Even though it's being updated, but somehow the most recent package in CRAN of this random forest SRC is not compatible with the latest version of R. So it took me some while. Eventually, I installed this package successfully using remote install GitHub, just using that link directly to install this package. So I'm going to load it in here. And also load in the survival package, set a random seed, create a data set. This must be a survival data set, so you have survival time, status. You have three predictors, x1, x2, x3. x1, x3 are continuous. X2 is categorical. So first we fit survival random tree, a random forest. So we use rfsrc function. The syntax is exactly the same as in other survival packages. It's a serve time status, tilde x plus 1, x1 plus x2 plus x3, and data equal to the same data. Number of trees equal to 500. Node size 15. Number of splits equal to 10, and we want variable importance. Okay. So here the number of the node size is the minimum number of observation required in a terminal node or leaf of each tree. Okay. You specify smaller value will lead to more splits and deeper trees, but that may create overfitting problem. The number of splits, the number of random split points to consider for each variable at each split. Higher value increase randomness and robustness. Okay, so we can print it out. You can see here, you got a sample size, number of deaths. So that's the number of events in the survival data set. Number of trees, 500. You can change that. The increase that number, you get more complexity in the trees, but takes more computational time. Okay. You get terminal node size 15 and an average number of terminal nodes in this random survival random forest just fitted is about 22. Number of variables tried at each split is 2. Total number of variables 3. And resampling used to grow trees, this SWOR is sampling without replacement. Okay. Resample size used to grow trees 316. Analysis RSF is I think let's see here. RSF is the random survival forest. Okay. And log rank, the splitting rule is the log rank plus random. That means we're using the log rank test as the splitting criteria with a random element to select the split point. Okay. The OOB CRPS is the OOB out of bag continuous rank probability score. And the OOB standardized CRPS is you scaled it to 0, 1. And the closer this standardized CRPS to 0, the better. So that's a model fit, it's better. OOB requests the performance error, that's our prediction error. The lower, the better. Okay, so this is kind of the interpretation of this print out of the random forest, survival random forest. Okay. And we can plot it out. We can do that plot. It shows you the number of trees and the error rate. It goes down. So you can see actually using 300 trees is pretty good already. Okay. Beyond that, it doesn't really bring much more benefit. And you have the variable importance. X1 is the most important one. Okay. And then we can extract the importance values. You get these numbers. And you can see it's ranked x1, x3, x2. So x2 is the least important one. Okay. We can use the plot out the variable importance. So this is actually the marginal effect plot. Okay, so these are the plotting against the raw variables. You see these, I think, mortality or with regard to the raw x1, you get to the individual data points, and you got like a assembled curve, and x1, x3, and x2. Okay, so you can see that not much difference for x2. The x1, the curve is going up very quickly, so that's very important. Okay, but if you want the traditional partial dependence plot, then you can use this plot dot variable, but you specify partial equal to true. And this is the partial dependence. So this is also with regarding to x1, x3, x2, but this is like the effect of x1, say, on mortality after you kind of fix other variables at their average. You just integrate out other variables. Okay. So you can see this partial dependence. You can also plot out survival curves. Say for the first 10 subjects, we just select 10, otherwise it could be really messy. So the first one is the OOB survival curve. You can see individual curves, and you see an assembled curve. That's the thick line in the middle. And then up there, there's a green line. That's the non-parametric called Nelson-Aalen curve. So the purpose is you compare your assembled curve with that green curve there. If they're very much in agreement, that means your survival random forest is a good model fit. If they disagree a lot, then that means your model needs to be improved. Okay. And the second one, the OOB Brier Score. This is really for prediction accuracy. The lower, the better. It also has individuals and also has an assembled curve with a thick line. And you also look at the time trend. So it's doing okay very well at the beginning and going up, and then reach a peak and then drop down at longer like survival time. Okay, but overall, like the assembled line is really below 0.5. Okay, so prediction error is okay. The third one is the OOB CRPS. So this is again, you wanted the curve to be lower, and it has an assembled curve, that's the thick line. And also the other, you see those numbers like 50 to 75, 75 to 100. Those are you cut this CRPS score into the different ranges, and you look into the subgroups. So it looks like the higher this CRPS score, the less accurate the prediction is. Okay. And the last one is the OOB mortality versus time. And for this one, I don't know why. It's very simple. So these dark dots, they're the time points where the mortality were calculated. And here we only have one assembled line, straight line. So this is just saying the mortality risk increase over time. The slope is not very steep, so it's going up over time slowly. Okay, but we don't have really individual curves, so I don't know why, but this is what we have here. Okay, more functionality of that. We can have new data, and then we can predict on these new data points, and we can print out survival curve for the first new subject. So these are all survival analysis stuff. We can do confidence intervals around the variance. Important is the subsample function, so it's going to take some computing time, and then we can print them out. You can see it uses the non-parametric, parametric jackknife, those different methods, compute all the percentiles. Then from here, you can get the 95% confidence intervals. And also you can use so-called the maximal subtree analysis based on the minimal depth variable selection method. The minimal depth is the how close this node is to the root. So this is a kind of we're getting into the weeds. So I'm not going to get into the too much details, but this is one of the variable selection method. If you want to do variable selection, the command is max.subtree. I just put in that object of the random forest survival tree there. Okay. And it's finished, and then you can print it out. Give you it. I think all three are pretty important. And then you can get specific times. You can predict the survival at specific time points. Okay, so you I want to know what's the survival probability at that time point. You can use this, and also you can use extract and plot a single tree from the forest using get.tree the survival random forest object and tree.id equal to 1, so the first tree. And then you can print it out. It looks pretty messy. I don't like it. So plot is much neater. But it's gonna, yeah, this looks a lot better compared to the kind of the printout. It's too messy to see. But anyway, okay, I hope you like this video. This how to fit a random forest for survival time. Okay, and if you like the video, please like our video, click on notification bell, and subscribe to our learning channel. And please recommend our video to other learners. And feel free to ask questions or make recommendations. Thank you very much.